Good morning, student. Today we are going to learn geometrical isomerism. Geometrical isomerism is due to the difference in the relative spatial arrangement of the atoms or groups about the doubly bonded carbon atom. Just note that it is the important condition. Molecule should possess double bond or triple bond. For a compound to show geometrical isomerism, the following conditions are necessary. The molecule must contain carbon-carbon double bond about there is no free rotation. Each of the double bonded atom must attach to two different atoms or groups. For example, CAB double bonded to CAB or CAB double bonded to CBA show geometrical isomerism. Just see in this molecule, this carbon atom attached to two different atoms denoted by suffix A and suffix B. Similarly, the below carbon atom is also attached to two different atoms which are denoted with suffix A and suffix B. If we are going to pass a line through carbon atom, we clear cut see that both suffix A are in left side plane while both the suffix B are on right hand side. So that's why this type of configuration is known as cis isomer. Just see in this diagram, this carbon atom is attached to two different atoms which are denoted by suffix A and B. Similarly, this carbon atom is also attached to two different atoms which are also denoted with suffix A and B. In this case, just see that if we see left hand side plane, we have on upper carbon atom suffix B, while lower side carbon atoms have suffix A, and same thing is happen on right hand side, or we can simply say that both suffix A are present in opposite plane, or one can also say that both atoms B present in opposite plane. That's why it is known as trans isomer. Just see example of 2-butene. In this example of 2-butene, we clear cut see that both hydrogen are present in one plane while both methyl also present in right hand side plane. That's why it is the example of cis isomer of 2-butene. Just see in this case both methyl are present at opposite plane. So it is the example of trans-butene. Just see in this example, it is the example of malic acid. So just see here, both carboxylic COH present on right hand side plane. That's why it is the cis isomer. Now just see, same molecule is written here, but in this case both carboxylic acid group are present in opposite plane. That's why it is the trans isomer. It is also known as fumaric acid. Now we are going to learn EZ system of nomenclature. For doubly bonded compound CAB is equal to CDE, it is not possible to assign them cis and trans configuration. So in this case, we are going to apply EZ nomenclature. Just see in this compound, this carbon atom is attached to fluorine and bromine, while this carbon atom is attached to iodine and chlorine. So in this type of compound, we cannot apply cis and trans rule. So in this case, first give the priority. First select one of the carbon atom, then give priority to attach atoms to that which is attached to your carbon atom. Priority is given on the basis of atomic number. So in this case, bromine have high atomic number as compared to fluorine. That's why bromine gets first priority, fluorine gets second priority. In the next step, we have to see another carbon atom. This carbon is attached to iodine and chlorine. So in this case, first priority is then given to iodine and second priority obviously comes to chlorine, because iodine have high atomic number as compared to chlorine. Now just see, both high priority atoms are come in one plane, that is bromine and iodine comes in one plane, and both lower priority atoms which are attached to carbon atoms come in left hand side plate. So this type of isomer, it is known as Z isomer. Now same molecule is written here, but just see, in this case obviously bromine got first priority, fluorine got second priority. In this case iodine got first priority, chlorine got second priority. Now we draw a line which is passed through both the carbon atom. Just see here, both higher priority atoms which are attached to carbon atoms are present in opposite plane. That's why it is known as E isomers. Now we are going to learn conformational isomerism. Conformational isomers can be defined as a different arrangement of atoms which can be converted into one another by rotation around a single bond. It is important. Alkane can have infinite number of conformation by rotation around carbon-carbon single bond. Just see, it is the example of ethane, and if we fix this carbon atom and if we rotate this carbon atom, there are infinite number of possible arrangement which can be comes out. In ethane, two carbon atoms are linked by a single bond. For each carbon atom is further linked with 3 hydrogen atoms. If one of the carbon atom is allowed to rotate about a carbon-carbon single bond, keeping other carbon stationary, an infinite number of arrangement of hydrogen of one carbon with respect to those of other are obtained. All these arrangements are called conformation. Bond angles and bond length remain the same. Now we are going to learn Newman representation for conformers. So basically, while writing Newman representation for a ethane, we first have to draw a circle. The center of circle is considered as a front carbon atom. Then you have to draw a Y like this and put 3 hydrogen at the corner of symbol Y. Same thing is happen with your backside carbon of ethane. While writing this, you have to draw inverted Y like this and put 3 hydrogen atom like this. If the angle between these 2 hydrogen, that is front hydrogen which is joined to front carbon and hydrogen which is joined to back carbon, if it is a 60 degree, then it is known as staggered conformation of ethane. If angle between both the hydrogen, if it is a 0 degree, then it is known as eclipse conformation of ethane. Now this is the second method for the representation of conformation of ethane. It is known as Sawhorse method. While writing the structure of Sawhorse method, one have to draw first a single line. At the end of line, both end of line is considered as carbon atom. So this is your front carbon, this is your back carbon atom. Again draw a Y on front carbon atom and put 3 hydrogen like this. Then draw a inverted Y like this and put 3 hydrogen. It is known as staggered conformation of ethane in Sauer's method. If both hydrogen, all hydrogen comes parallel to each other, then it is known as eclipse conformation of ethane in Sauer's method, which is look like this. So just see here, y-axis denotes potential energy, x-axis denote rotation. From this diagram we clear cut see that staggered conformation possess low potential energy, while eclipse conformation of ethane possess highest amount of energy. The energy required to rotate a molecule about carbon-carbon bond is called rotational or torsional energy. It is important to note that eclipse conformation have highest energy. That's why eclipse conformation is a least stable. Now we are going to discuss conformational analysis of Nbutane with energy profile diagram. So it is the diagram for Newman projection for Nbutane. So while drawing Newman projection formula for Nbutane, one have to first draw a circle, put a dot here which is considered as first carbon, then draw a Y like this, inverted Y like this, and then draw a Y on backward carbon. So now put 2 hydrogen like this and 1 methyl group here. On backward carbon you have to put 1 methyl and 2 hydrogen. So this is first, this is second, backward third carbon, this is fourth. So it is the example of Nbutane, and it is the Newman projection formula for Nbutane. Now if we rotate backward side, the angle between this methyl and this hydrogen, it is 60 degree. It is known as anti-form or anti-conformer of Nbutane. If we rotate backward carbon by 60 degree, this hydrogen comes in front of this methyl, this hydrogen comes in front of this hydrogen, this methyl comes in front of this hydrogen. So it is known as partially eclipse conformer of Nbutane. If we again rotate it by 60 degree, so this hydrogen comes here, this methyl comes here, this hydrogen comes here like this. Just note that if the angle between 2 methyl, in this case it is 60 degree now, so it is known as Gauche conformers. If we again rotate this by 60 degree, we comes here, methyl in front of methyl, hydrogen in front of hydrogen, and this hydrogen in front of this hydrogen. So it is known as complete eclipse conformer of Nbutane. If we again rotate backward carbon by 60 degree, just see here, angle between this methyl and this methyl is now 60 degree. That's why it is known as Gauche conformer. If we again rotate this methyl, if we again rotate backward carbon by 60 degree, then we come arrangement like this, which is similar to this arrangement, and that's why it is known as partially eclipse arrangement. So now we are going to discuss energy profile diagram for Nbutane. So in energy profile diagram, we see that anticonformer have least potential energy and complete eclipse conformer have highest amount of potential energy. It simply means that complete eclipse conformer is least stable. Anticonformer is most stable. Partially eclipse conformer have 14.60 kilojoule more energy as compared to your anticonformer. Now again see that when we go from partially to Gauche conformer, we see that there is a decrease in energy. It simply means that Gauche conformer is more stable than your eclipse conformer, but it is least stable than anticonformer. So order of stability of conformer in Nbutane is anticonformer is more stable than Gauche. Gauche is more stable than partially eclipse. Partially eclipse is more stable as compared to completely eclipse. It simply means that anticonformer possess least potential energy and complete eclipse conformer possess high potential energy. Thus, at ordinary temperature, N-butane molecule exists predominantly in antiform with some Gauche forms. Now we are going to discuss conformation and configuration, difference between them. Conformation of molecule are different spatial arrangement of its atoms and groups that arises due to the rotation of part of the molecule about a single bond. It is important. Now configuration of the molecule is spatial arrangement of atom or group of atoms about a rigid part. It is important, about a rigid part of the molecule, that is above double bond or ring and a chiral part of the molecule. In conformation, there is a low energy barrier which varies from 4.2 to 4.6 kilojoule per mole. Difference of energy between two configuration is more than 34 kilojoule per mole. Conformers are non-isolable. It is important. Configuration are isolable. Conformation are easily interconvertible. They get converted even at a room temperature. It is important. Configuration are not easily interconvertible. Interconversion of conformation involve rotation of part of molecule about a single bond. Interconversion of configuration involve bond breaking and bond reforming process. It is important. A molecule could have infinite number of conformation. A molecule can have only one configuration, that is different configuration, different molecule. Thank you very much.